Okay, in this problem, we're asked to, for each critical point, P, use Morse lemma to write f after a change of coordinates in one of the following three forms. So the first form is f of p plus u squared plus v squared. Second form is f of p minus u squared minus v squared, or as f of p plus u squared minus v squared. And we're given, and we also want to describe what the level curves are like near p. And we're given that f of xy is equal to the quantity x minus 1 squared plus y plus the quantity y plus 2 squared plus x minus 3y. So first, let's figure out what the critical points are. So the partial derivative of f with respect to x is 2 times the quantity x minus 1 plus 1. And f sub y is 2 times the quantity y plus 2 minus 3. And we want to find when our gradient vector is equal to 0, or when each of its components, and hence f sub x and f sub y, are equal to 0. And we find that x is equal to 1/2. Y is negative 1/2. And we want to now calculate what the Hessian matrix is and the determinant of it at our critical point. So partial derivative of f sub x with respect to x is 2. Partial derivative of f sub x with respect to y is 0, and likewise, partial derivative of f sub y with respect to x is also 0. And then finally, the partial derivative of f sub y with respect to y is 2. So we have our Hessian matrix is given as 2, 0, 0, 2. And we want to find the determinant of that. So we'll say D. Our determinant of our Hessian matrix is just 4, 4 minus 0. And we want to now use Morse lemma. We have non-zero determinant, so we know that we have non-degenerate critical point at 1/2, negative 1/2. And Morse lemma tells us that lambda 1 times lambda 2 is equal to 4. Lambda 1 plus lambda 2 is equal to f sub x plus f sub y, which is equal to 4. And so we can solve these simultaneously. We see that lambda 1 is equal to lambda 2 is equal to 2. So we have two positive lambdas, and our Hessian matrix is also positive, or the determinant of our Hessian matrix is also positive. So that tells us that we are using the first case at our critical point. So we know that we can write f composed of our change of coordinates, phi of uv, is equal to f at the point 1/2, negative 1/2, plus u squared plus v squared. So we can calculate f at 1/2, negative 1/2, and we get we're just plugging in 1/2, -1/2 into our function right here, f of xy, and we get 9/2 plus u squared plus v squared. Sorry, this should read f composed of phi rather than f phi phi. I don't know why I wrote that, but f composed of phi phi, or f composed of phi at uv is equal to 9/2 plus u squared plus v squared. So it's important to note that Morse lemma just tells us of the existence of this change of coordinates. It's not necessarily going to be easy to calculate what that change of coordinates will be, but just for the sake of the fact that we can, I'm going to go ahead and calculate that in this case. So start off with expanding out our f of xy. So multiplying out this square, we get x squared minus 2x plus 1 plus y squared plus 4y plus 4 plus x minus 3y. So we can combine the x terms. We get combine the y terms. We get and then combine our constants. Get plus 5. And now we can do what we might expect, just complete the square. So we get the quantity x minus 1/2 squared minus 1/4 plus y plus 1/2 quantity squared minus 1/4 plus 5. We can combine these constant terms. And we see that we get a nice function in terms of our f of p, which is 9/2. And then x minus 1/2 will let as u. And for our v, we'll just let that be y plus 1/2. So we see that if we let that be the case, we have our f composed of phi of uv is 9/2 plus u squared plus v squared. And we have our change of coordinates. And we used Morse lemma to write f in this term, or in this form at p.